Example 5, a trig equation involving multiples of an angle. We want to consider the equation 2 sine 3 theta minus 1 equals 0. We want to find all solutions of the equation and find the solutions in the interval 0 to 2 pi. So for A, finding all solutions of the equation. We can solve this equation just like our previous examples. What may be confusing though is that the equation contains a multiple of an angle, sine 3 theta. To make solving this equation easier, we can substitute u equals 3 theta. Thus we get 2 sine u minus 1 equals 0. We can isolate the sine u term and then solve for the angle u in the interval 0 to 2 pi. Thus we get u equals pi over 6 and 5 pi over 6. To get all solutions, we add integer multiples of 2 pi to these solutions. We need to make sure to do this step before solving u equals 3 theta. So we get u equals pi over 6 plus 2k pi, and u equals 5 pi over 6 plus 2k pi, where k is any integer. Now we need to solve for u equals 3 theta. We can do this by dividing our solutions by 3. So we substitute back in 3 theta equals u. Thus we get 3 theta equals pi over 6 plus 2k pi, and 3 theta equals 5 pi over 6 plus 2k pi. We divide by 3, and we end up getting theta equals pi over 18 plus 2k pi over 3, and theta equals 5 pi over 18 plus 2k pi over 3, where k is any integer. Now we need to find the solutions in the interval 0 to 2 pi for 2 sine 3 theta minus 1 equals 0. By plugging in integer values of k, we can find all solutions in the interval 0 to 2 pi. These solutions correspond to k equals 0, k equals 1, and k equals 2. For all other values of k, the corresponding values of theta lie outside the interval 0 to 2 pi. So the solutions in the interval 0 to 2 pi are shown below.
In example 6, we're going to consider the equation square root of 3 tan theta over 2 minus 1 equals 0, otherwise a trigonometric equation involving half angle. So we're going to first find all solutions of the equation and then find the solutions in the interval 0 to 4 pi. To find all solutions of the equation, we can solve this equation just like the previous example. To make solving this equation easier, we can make the substitution u equals theta over 2. Thus we get square root of 3 tan u minus 1 equals 0. Now this equation looks much easier to solve. Isolate the tan u term and then solve for the angle u in the interval negative pi over 2 to pi over 2. Remember, we always solve arc sine of x and arc cosine x in the interval 0 to 2 pi, while we always solve arc tan x in the interval negative pi over 2 to pi over 2. Solving this out, we get u equals pi over 6. Since tan x has period pi, to get all solutions, we add integer multiples of pi to these solutions, thus getting u equals pi over 6 plus k pi. Now we need to solve for u equals theta over 2. We can do this by multiplying our solution by 2. So u equals theta over 2, we substitute that back in to get theta over 2 equals pi over 6 plus k pi. Multiplying this equation by 2, we get theta equals pi over 3 plus 2k pi, where k is any integer. Now we'll find the solutions in the interval 0 to 4 pi. By plugging in integer values of k, we can find all solutions in this interval. These solutions correspond to k equals 0 and k equals 1. For all other values of k, the corresponding values of theta lie outside the interval 0 to 4 pi. So the solutions in the interval 0 to 4 pi are x equals pi over 3 and x equals 7 pi over 3.
Now on to example 7. So we want to consider the equation secant theta tan theta minus cos theta cotan theta equals sine theta. We want to find all solutions of the equation and find the solutions in the interval 0 to 2 pi. So for A, finding all solutions of the equation. This equation is pretty tricky to solve. We should try to use strategies we used in previous examples to approach this problem, combining like terms, factoring where we can, making substitutions, putting the equation in one term, and using trig identities. Recall the reciprocal trig identities. Secant theta equals 1 over cos theta, tan theta equals sine theta over cos theta, and cotan theta equals cosine theta over sine theta from previous chapters. We can use these identities to write the given equation in terms of sine theta and cos theta only. This should help us see what process we should take in solving this equation. So when we make these substitutions, we end up with sine theta over cos squared theta minus cos squared theta over sine theta equals sine theta. Now that we've substituted in our reciprocal trig identities and combined like terms, it might help to add the cos squared theta sine theta term to each side of the equation. This way we can end up with a single term on either side. There's more than one way to solve every equation, but we should try this idea first, and if it doesn't work, we can try something else. To combine the terms on the right side of the equal sign, we can multiply the sine theta term by sine theta over sine theta, which is just multiplying by 1, and combine the two fractions. Thus, we end up with sine theta over cos squared theta equals sine squared theta plus cos squared theta over sine theta. In the numerator of the right side fraction, we have sine squared theta plus cos squared theta. Recall the Pythagorean identity, sine squared theta plus cos squared theta equals 1. We can use this substitution to make solving our equation easier. When we substitute 1 in for sine squared theta plus cos squared theta, we get the equation sine theta over cos squared theta equals 1 over sine theta. Next, we can cross multiply to get rid of the fractions, and we're almost finished. We'll end up with sine squared theta equals cos squared theta. Finally, let's put all our terms in terms of either sine theta or cosine theta. Again, we can use the Pythagorean identity, sine squared theta plus cos squared theta equals 1, rewritten as sine squared theta equals 1 minus cos squared theta. Now we can substitute this identity into the sine squared term to get the entire equation in terms of cos theta. We end up with 1 minus cos squared theta equals cos squared theta. When we work through this, we get a plus or minus the square root of 1/2 equals cos theta. Since we took the square root of each side of the equation, we need to make sure to include the plus or minus sign. Now we can solve for theta in the period 0 to 2 pi. So when we solve through this, we end up getting theta equals pi over 4 and theta equals 3 pi over 4. Since cos x has period 2 pi, to get all solutions, we add integer multiples of 2 pi to these solutions. What we end up with is theta equals pi over 4 plus 2k pi, and theta equals 3 pi over 4 plus 2k pi. So for part B, we need to find the solutions in the interval 0 to 2 pi. We can do this by plugging in integer values of k, and we can find all solutions that are in this interval. These solutions correspond to k equals 0 only. For all other values of k, the corresponding values of theta lie outside the interval 0 to 2 pi. So the solutions in the interval 0 to 2 pi are theta equals pi over 4 and theta equals 3 pi over 4.